Welcome back, everyone, to Lecture 9 of a series on molecular simulations and statistical mechanics. Today, we're going to be talking about something called a thermodynamic process, and we're going to look at alternative formulations of the thermodynamics we've done so far. So in previous lectures, what we've studied is specifically these entropy postulates. We postulated the existence of some function which was maximized at equilibrium, and it was a function of other extensive variables of the system, like the internal energy, the entropy, or the internal energy, the volume, and the number of particles. So from that, we were able to derive a lot of very interesting results. We found the Gibbs-Duhem relation. We were able to show things like the Gibbs phase rule, and also look at different forms of the first law of thermodynamics. But now the question is, how do we really think about thermodynamic processes in sort of an alternative way, or in a different sense than perhaps what we've discussed so far? So we've been concerned with these equilibrium states. And recall that equilibrium was when we allowed a closed system to sit long enough in time that it could reach some sort of steady state and sort of just fluctuate, have small fluctuations around what are known as equilibrium values, right? Well, in general, when we look at this, at systems, they're not necessarily going to be in equilibrium. And the fundamental relation which describes the system is actually going to be this manifold in space. So a manifold, it's actually not as scary as it sounds. It's just a multi-dimensional function. Multi-dimensional function. And so we can draw manifolds just the same way we do functions, but we're going to have higher dimension spaces, right? So really, when we think of the fundamental equation in the entropy, which was a function of the internal energy, the volume, number of particles, right? What we can do is we can think of S as being, let's say, on the z-axis here, and U as being on this x-axis. And what we're going to do is just lump everything else and just say, like, okay, yes, this is higher dimensions than 3, but we're just going to put all of them over here. So this is just going to say, this is parameter x sub I, if you have multiple n's or something like this, in a particular direction, right? Whether that's the number of particles or the volume. So J is indexing over things like that. So J would be something like volume or N, and then I would be within something like N, right? You'd have maybe P total particles or something. Something like that. So recall that in our postulates, we required that partial S, partial U be bigger than 0. It could only equal 0 at equilibrium, right? So equal 0, and this would be at equilibrium. Equal 0, right? And we also required this manifold to be continuous and single valued. Continuous and single valued. So if the derivatives with respect to S are always positive, unless you're at the maximum of the manifold, it's continuous and single valued, then we can actually draw it in a very specific way. I'm going to change color here. So, of course, you could prove this structure mathematically, but you can sort of think here where we're going to have some manifold that comes up. Let's say here's the maximum, right? I guess we can make that a solid line. So you can imagine you have some sort of manifold like this in these axes, right? And this manifold is essentially the solutions to this fundamental equation, right? Now, in general, when we're moving around on this manifold, right, if we're just going to trace out a path, this is what's known as a thermodynamic process. So our system may start somewhere on this manifold and then start moving along it, right? Now it can only trace along the manifold. You know, maybe it goes and it reaches, you know, a state of equilibrium somewhere, right? Any process that travels along this manifold is called a quasi-static process. All quasi-static means is that once there's a change in the system, once there's some perturbation in the state of the system, that all of the system essentially re-equilibrates to that state instantaneously. So although it may not be in equilibrium, it's still quasi-static in the sense that it's reorganizing its state very fast, right? Now, of course, in real physics, right, real physics happens in non-equilibrium states. And in fact, in general, real processes are reversible, which we haven't introduced yet. So the idea now of reversibility, let's introduce reversibility. What is reversibility? Reversibility is the idea that if you start at some state, let's say you start at some state A, and then you go along this manifold, let's say to another state B. The idea of reversibility is that if you can travel from A to B along this curve, so if you go from A to B, you can then go back, right? You can then go back to A. So let's think about what types of processes would be reversible. Well, in terms of these manifolds, reversibility can only occur if the change in your entropy, so let's say we had this was the initial entropy of the system SA. If the change in entropy going from A to B is negligibly small, so this has to be approximately equal to SB, then it is possible to go back and forth along this process. And we have what's known as a reversible process. So if SB is approximately equal to SA, and they go along that exact entropy value for the entire path, then the process is reversible. Now, irreversible processes, which is most of thermodynamics, occur more like what I drew originally, or if you started at A, let's say, and you traveled with non-constant entropy up this manifold, right? Let's say you travel to C or something. This is irreversible because there's an entropy change. So this is an example of an irreversible process. So now using our diagram, let's try to think about some of the stuff we've talked about before in this class, right? So we have this concept of reversibility being constant entropy processes, irreversibility being non-constant entropy processes. But now let's sort of think about our thermodynamic postulates we've introduced. I'm just going to erase these here. So in our thermodynamic postulate, we made an assumption, we postulated that the entropy was maximized at equilibrium. So what does that mean? Well, we can think about it as if we took a constant energy. So let's take some value for the energy here. Let's say it is right here. Let's see. Let me draw this really well. So there's, in the constant energy and constant additional variables case, what we carve out along this manifold is some function, right? So this is going to carve up and then hit and then come around just like that, right? All the entropy maximum postulate says that if you start a state somewhere in here, so let's say state A, that the system is going to evolve towards a maximum entropy state. So it's going to evolve along this path in a quasi-static process until it reaches equilibrium, right here. So this is the entropy maximum postulate. Now, because of the shape of this function, we actually also have an energy minimum postulate. You can see that by taking, for instance, I just grabbed the same color. Let's do a different color. If you look at the system at constant entropy, so let's say here, constant entropy would come across like this, right? And then it would carve out some function along this s-axis. All that the entropy minimum postulate says is that if you start somewhere in here at a specific constant entropy, let's say S prime, and you start somewhere on this manifold, that you're going to evolve to minimize the energy. So notice this is the minimum energy of the system. And I guess you could think of that because this is U in the negative direction in the way I've drawn it. But really, what you want to think about here is that when you look at these fundamental relations and you think about how we've postulated that the entropy and the internal energy are related and the fact that they're a continuous single-valued function, you can clearly see that anywhere where you fix, you fix the conditions of everything else and you look at the paths that move along, you will maximize entropy along that path and you will minimize energy, right? So this is really interesting. And this is not a formal proof, but I think it's easier to see graphically and just, intuit what's going on here. So in general, every system is going to have some sort of manifold like this, and thermodynamic processes are going to evolve along this manifold in very, according to these specific directions, according to whatever in the system is allowed to change, whatever's allowed to, fluctuate. But in these cases in which we fix everything but the variable of interest, it's really easy to see kind of how this evolution will occur. So this is just a quick introduction to thermodynamic processes and sort of how we get to the concepts of them from the idea of the postulates we introduced earlier. And then of course, introducing things like reversibility, which are constant entropy paths, and irreversibility, which are non-constant entropy paths. So we sort of have a good gist of what's going on with these types of processes. And of course, this is just an introduction in which we'll actually go talk about some more complex ideas of thermodynamics once we get into statistical mechanics. Now, we've talked a lot about fundamental relations, right? We've talked about entropy, we've talked about internal energy, but really these quantities are kind of odd. They're strange. They're not something that we really observe in everyday life, right? So experimentally, it's not like we just can gain access to these properties. Usually it's a lot easier to deal with things like temperature or pressure. And those are things we can actually go into a lab and measure, right? We can use a barometer or a thermometer. We can actually determine these properties. We can't directly determine entropy and internal energy. So what we want to do is we want to understand how we could rewrite the fundamental relation in terms of variables that we can measure, right? So in terms of your temperatures and your pressures, so we want to go from here, but we want to preserve all the same information. So we want to go from SU to things like temperature and pressure while preserving all information. We want to preserve all information in this process. Now recall that things like temperature and pressure have partial derivative definitions with respect to these other variables, right? Like we know that T, for instance, can be written as partial U, partial S at constant V and Ni, right? Minus P was partial U, partial V at constant entropy and Ni, right? Now, we encountered something earlier in the class that allowed us to take something like a fundamental relation or a function of some variables and convert it to a new function which had an argument switched out with its derivative with respect to that argument. When did we use this? Well, we used this when we looked at taking the Lagrangian into the Hamiltonian form. Well, this is the exact same process, right? We want to do the exact same thing, so we're going to invoke the mathematics that we used before in the Legendre transform. So the Legendre transform is going to take us from these very sort of abstract ideas about energy and entropy and be able to convert them into things like Helmholtz free energy, which we can write as functions of temperature, volume, and number of particles. Much more intuitive properties to think about, right? So let's recall how we did a Legendre transform. So in a Legendre transform, really what you have is you have a function, right? And remember, we wanted to describe this function by the derivatives, so the slopes of the tangent lines, and the intercepts of those tangent lines with some axis, right? So we wanted to kind of define what we called before as an envelope. Probably should have used a different color here, but this is mostly a reminder, right? So the idea here, let's say in this example, we'd have something like internal energy. We want to replace the entropy part, so that would be on the x-axis. We look for the derivatives of each of these lines, which are the slopes at each specific value, and then we compute the intercepts, which are just the new function f. So if you recall, the mapping was actually not that difficult. We simply just found the equations for these lines and rearranged to solve for the intercept. So let's go through that procedure one more time just to make it really clear. And of course, you recall we can do this in as many dimensions as we want because these derivatives are basically independent of each other, right? These partial derivatives. So how do we find the equation for a line? Well, we said, okay, this tangent line, right, we'll call this y, has the equation of y equals mx plus b, right? All right, well, let's write it in terms of the variables of the problem, right? So y, right, in this case, is u at whatever, specific s. So we'll say, let's say we're at s1, right? So whatever this u is, u of s1, equals the slope of the line, which is just the derivative of u with respect to s at constant everything else, right? Volume, number of particles, evaluated at s1, plus b, which is the intercept here, which we're calling f, plus f. So how do we solve for it? Well, we simply just rearrange the equation. We say f is equal to u minus partial u, partial s, xi. Now, of course, we have, and it looks like I forgot this x in here, right, which you remember was just s1, right? S1. So this is for this specific point, right? And I guess we should be more specific and say this is F1, U1, right? Where U1 is U at S1. Now, of course, if I solve all of these, the entire function can be written as F equals U minus partial U, partial S, at constant, all the other variables in the system, volume, number of particles, times S, times the entropy S, right? Well, this is simply the definition of the Helmholtz free energy. To see that, you may have seen this in your undergrad thermo class. F equals U minus TS. You can also write this, since we know U, let's see. I think I'm going to run out of space here. So I'm going to erase this board, but really what you can see is that this Legendre transform is once again becoming extremely important to writing these new functions. And really what we've been able to do is take something that doesn't make a lot of sense, like entropy as a function input, and convert it to something that makes a lot more sense, temperature, right? And it was really easy. All we had to do was find the equations for this manifold, or for this envelope that describe the function. And that leads us to this. So I'll just write here for completeness that this is the Helmholtz free energy. So I was always confused where things like Helmholtz and Gibbs free energy came from, but really all they are these alternative formulations written with a Legendre transform to replace the arguments of the internal energy function with arguments that make more sense to us, or that are just different. Continuing with this example, we've just found an equation, F equals F of T, V and N, and we found it to be equal to U minus TS. Well, let's think about what the total derivative of F is now. You'll see this is kind of a theme in the class. We look at how these things change, right? And how that modifies all the other parameters. When we do this, we just use the chain rule, right? Which we've gone through a lot already in the class, so this should be pretty familiar. Partial F, partial N. And of course, you have a sum over all these n's here. This is T and V. D and I, right? Okay, that's good enough. But what else is dF equal to? Well, if we look at this expression, so this is expression 1, and I guess we'll call this 1 star because we've just modified it, right? Well, 2 star dF computed from this equation, well, that's just du minus TdS plus SDT. Minus SDT, right? But if we recall that the internal energy is equal to, or the change in internal energy is equal to TdS minus PdV plus the sum from I equal 1 to the number of constituents in the system of mu I dN I, right? Well, we can just substitute that back in and get an equation for dF, right? We have TdS minus PdV plus sum equal 1 to n of mu I dni. And now we have a minus TdS minus SDT. Well, this TdS and this TdS are going to cancel, and that's going to leave us with an expression minus SDT minus PdV plus the summation over all of our mu I dni's. Right? So we now have an expression for the change in F as a function of these variables. Now, what does that mean? Let's do what we did last time with the internal energy and make a comparison here. We know that this is dF, and we know that this is dF, right? Well, that means partial F partial T by inspection must be paired with a dt. Minus S is paired with dt, so we can derive the expression that the change in the Helmholtz free energy with respect to temperature at constant volume and number of particles is equal to the minus entropy, right? We can do this similarly for each term. We can go and say, okay, partial F partial V at constant T and Ni is equal to minus P, right? And finally, we can look at all these other terms and say that partial F partial Ni at constant temperature and volume, well, those are just equal to the mu i's, right? And so you've seen we've been able to derive actually some really cool relationships here with really not much work. All we needed was the entropy maximization postulate, postulating the fundamental relation, rewriting that fundamental relation in a new way using a Legendre transform, and we can get to these new properties, right? So remember, S now is written as a function of a partial derivative. Before, we had a partial derivative of the internal energy with respect to S gave us temperature. And look, now it's switched, right? So now when you run an experiment, if you can gain something like the Helmholtz free energy and you can study it as a function of temperature, you can actually estimate the entropy, right? So these sorts of relationships are extremely important in molecular simulations because we can actually leverage them to calculate quantities that are not easy to calculate, such as entropy, right? The last thing I want to show you guys today are the Maxwell relations. So the Maxwell relations, you've probably used them. Usually I feel like you're given a table of Maxwell relations and then asked to do some little thermodynamic calculation. But let's just think about what the Maxwell relations are, right? So consider the internal energy, and I'm going to leave off the n terms for now because we're going to look at just some mixed partials on temperature and pressure here. So partial S, constant V, ds, right? Minus partial U, partial V, or actually this will be plus partial U, partial V, at constant entropy, dV, right? So let's think about this, right? We have a partial derivative of U with respect to S, partial derivative of U with respect to V. What happens, so let's take this term. This is temperature, of course. But let's look at it. Partial U, partial S at constant V. What if I take the partial derivative of this quantity with respect to V? Okay, we'll just, that's some quantity, whatever, right? Now let's look at this one. Partial U, partial V. And this time, I take the partial derivative with respect to S. The question is, how can we relate these two? Well, for the specific types of functions that we're dealing with, we can actually just flip the direction of these partial derivatives, right? So what we can do is we can actually, instead of writing partial V, partial U, partial S at constant volume, we can actually write partial S of, or that this is equal to partial S, partial U, partial V at constant S, right? And equivalently over here, right? So if these are equal to each other, right? Because you can see here we have that they're equal, right? Then we can write them in a slightly different way, right? Well, if they're equal, then we can actually invoke these definitions. So this was minus p, right? This is t. These are equal to each other. So what that means now is that the partial derivative of t with respect to v at constant s, this is this left-hand side here, is equal to partial or minus partial p partial s at constant v. This is a Maxwell relation. This is a Maxwell relation. Now, of course, we could have done this procedure on any number of quantities, right? Like, really, in principle, you could even ask, okay, how many of these mixed partial derivative equivalencies are there, right? Well, the idea is, if you had something like t plus 1 variables, the total number of Maxwell relations that you can derive in the way that we just derived this one, right, is t times t plus 1 over 2. These are all of the separate pairs of Maxwell relations we could derive. So this is equal to the number of Maxwell relations. Right? And you can see all we did was notice that we could flip the direction of these partial derivatives, and by using the definitions we had come up with earlier, we could just write new relationships, right? So the Maxwell relations can be really important. And really, I guess, to summarize what they are, a Maxwell relation, I probably should have written this first, but a Maxwell relation, they are expressions relating mixed partial derivatives. So relating mixed partial derivatives of thermodynamic quantities. Now, I didn't even really need to write this definition for du to show you this, but I was showing you, if you had something like du and you had an expression, this is how you could relate these two together, is by going down, taking that extra partial derivative on each side that the other one doesn't have, flipping their direction, noting that those are equal, right? And then invoking the definitions to then gain some new insight, right? Okay, so I've written an example up here, and essentially in this example, what we're saying is that given that the coefficient of thermal expansion, alpha, is equal to 1 over b partial v partial t at constant p, if alpha is equal to 1 over t, show that the constant pressure heat capacity, defined as T over N partial S partial T at constant P, is independent of pressure. So the solution will begin by just plugging in our given information, right? So we have 1 over T is equal to 1 over V partial T at constant P. Now we need to look at a Maxwell relation to try and cast this V in terms of entropy, right? So what we're going to do is we currently have something that looks like partial V, partial, and now T is partial U partial S, right? And we want to ask how we can flip this around, right? So the question is, how can we write this? If we invert this, so let's invert it, we could write this as partial v of partial u partial s, right? This is as if we flipped this equation, right? I need to think under what conditions you're actually allowed to do this, but with thermodynamic quantities, I believe you are. I could be wrong, however. So essentially, if you take this and you flip it, right, you could say that this is equal to partial s of partial u partial v. Well, this is just equal to minus partial p partial s. Well, if the flipped version is equal to this, then we can flip it back to make it equal to our original guy. So that would equal minus partial s partial p, and this would have been at a constant temperature, right? So we know that minus partial s partial p at constant t is equal to partial v partial t at constant v. Okay, so let's substitute that in. We now have this expression will multiply by v on both sides. So those will cancel. So we'll have v over t is equal to, and now we'll make a substitution, minus partial s partial p at constant t, right? Now we can convert this into a useful form by multiplying both sides by t. That'll take us to v equals minus t, and now we have partial s partial p, constant t. Now let's take the temperature derivative. So we're doing the mixed partial derivatives here, so partial t. That's going to leave us with partial v partial t is equal to minus t partial t of partial s partial p at constant t minus partial t, which is 1, so that's partial s partial p t, constant t. Well, remember, this guy is just equal to this guy, right? So we're re-invoking this Maxwell relation. By doing so, we end up just being able to add this to both sides. So we'll add this partial s partial p to both sides. Those will cancel out because they're equal to each other, right? And all we're going to be left with is this equals 0. Let's see, I'm going to rewrite this up here. So what we've gotten to is that 0 equals minus t times partial t of partial s partial p at constant t. Well, now we can reverse the direction of the partial derivatives, right? Partial s partial t at constant p. Now recall, if we keep things fixed in the system, we can just multiply by t over n on both sides and put it inside this derivative because it's a constant. So we can get that 0 is equal to minus t partial p of t over n times partial s partial t at constant p, right? Well, this is just equal to the heat capacity now. So that implies that 0 equals minus t partial p of Cp. Well, if t is non-zero, that means partial Cp partial p must be 0. Well, all that means is that Cp is independent of pressure, and we're done. So in this example, we used the Maxwell relations. So we using this interesting quantity here, we derived a Maxwell relation with respect to the entropy. And I'm actually not 100% sure if the way I derived it is perfectly correct. I need to look into this because I'm a little suspicious about this inverting it and flipping things with derivatives. But for now, if we take that as the way we can derive the Maxwell relation, we can go through, we can invoke the Maxwell relation again to eliminate variables, and we can express certain properties about things like the heat capacity with respect to other properties like the isothermal compressibility. So the Maxwell relations are extremely important. I don't want to go into them too much further because you can really figure these out on your own. All they are the equivalences between mixed partial derivatives of thermodynamic quantities, and they will pop up a lot, but just if you've seen them once, I think that you're prepared to start looking at the literature in molecular simulations and how they're implemented there. So thank you guys very much. Our next lecture will be our last lecture on thermodynamics. We're going to sort of close everything out. We're going to talk about things like thermodynamic stability and also, I believe, Jacobian transformations. So looking at how we can actually use Jacobians to do interesting thermodynamic problems. And after that, we are ready to dive into statistical mechanics. So thanks again. We'll see you next time.